So now we are going to see why silicon carbide MOSFETs are being preferred as compared to silicon IGBTs. What is the advantage that silicon carbide MOSFET offers, or rather why carbide MOSFETs are available for voltage ratings where earlier it used to be silicon IGBTs, not silicon MOSFET, right? So what is the combination of silicon carbide and MOSFET which makes it better than the silicon IGBTs? So if you refer to one of my previous video, then you can quickly see the structure of a MOSFET and how and what is the advantage of going for an IGBT structure over a MOSFET structure, especially when we talk about higher voltage and currents. So that makes it clear that for MOSFETs, as we keep on increasing the blocking voltage of the MOSFET, the depletion region length also increases. So as we increase the voltage rating, blocking voltage capability, the depletion region length also increases, which leads to increase in the resistance of this N minus region, which essentially increases the conduction losses. So at one point comes where we can no longer afford to increase the resistance, and then we change this N layer to P layer, and the structure becomes that of an IGBT, and then we get the advantage of minority carrier devices in terms of reducing this resistance of the N minus region. Now, how things changes if we talk about silicon carbide. So silicon carbide is a wide band gap device which offers much higher critical electric field. So it offers much higher value of critical electric field as compared to silicon. In simple word, what it means is if you want to block 1000 volt, then if you need this much length of silicon to block that 1000 volt without creating a breakdown of this material, for silicon carbide a much smaller element is good enough to block the same voltage. That is what it means by when we say that it has much higher value of critical field strength as compared to silicon. So now if we apply this principle onto the diagram, then if you are making a MOSFET, earlier we discussed the structure, right? If you are now making a MOSFET of silicon carbide instead of silicon, in that case, obviously as we increase the V rating, our L will increase, but our L will still be much smaller than the length in case of silicon, and therefore the resistance of the N minor region also we expect smaller, assuming the same resistivity. Again, that might make somewhat of a difference, but predominantly we expect the resistance also to be much smaller as compared to the silicon, and therefore the need to utilize the conductive modulation by putting a P region gets pushed forward. So instead of 100 volt, instead of 200 volt, instead of 500 volt, 600 volt was roughly the limit where we start thinking that look, it is better to go for IGBTs in silicon as compared to the MOSFETs in silicon. But for silicon carbide, you can keep going further because your depletion region length is small, so your resistance is still comparatively small. And that is the reason you see silicon carbide MOSFETs are available of 1.2 kV, 1.7 kV, even 3.3 kV. On the other hand, this is the region in conventional silicon was predominantly by the IGBTs and not by the MOSFETs. So that is why you see both. Now the question comes that if you have a higher voltage silicon carbide MOSFET, would you prefer to use that, or would you prefer to use a higher voltage silicon IGBT? Of course, one of the advantage which is pretty obvious here is because of the MOSFET structure itself, it can switch much faster. There is no tailing current which is present in IGBT, and therefore at a very basic level it makes sense to see the benefit of using a silicon carbide MOSFET even in the voltage ranges of 1.2, 1.7 and 3.3 kV as compared to silicon IGBTs of similar voltage ratings.